In section 6.5, we're going to learn how to calculate the lengths of curves. So if we start with the function y equal f of x, and we are interested in finding the length of the arc, from the point where x is equal to a to the point where x is equal to b. So here's what we're going to do. We're going to divide our interval from a to b up into equal subintervals. Okay, pretend those are equal subintervals. And we're going to take a look at little sections of the curve. And what we're going to do is get an approximation for each little piece, add up all those approximations, and we'll have an approximation for the entire length. So if we focus in on one little piece of this curve, so let's say I'm going to focus in on this piece right here. Let me draw that so it's a little bit bigger. So here's our curve, and here's one endpoint, here's the other endpoint. Now what we're going to do is we're going to use straight line segments to approximate the length of the curve. Now, the length of that line segment can be found using the Pythagorean theorem. Okay, this measurement across the bottom is the change in the x coordinates, and if we've got the ordered pair for the 2 points, we can certainly find the change in the x coordinates. This line segment here represents the change in the y coordinates. Okay, and the change in x, of course, is going to be the same for each little piece. The amount of change in the y values is going to be different for each section. So we can say that the length of that line segment is the square root of the change in x squared plus the change in y squared. All that is the Pythagorean theorem. So then the length of the entire curve, let's call that L, will be approximately equal to the sum of all of the lengths of our little line segments. So let's say the sum, if k starts at 1 and goes to n, of the square root delta x squared plus delta y sub k squared. Now again, I'm using delta x because that's going to be consistent over no matter which interval we're looking at. The change in x is the same. I've written delta x with a subscript of k because, delta y with a subscript of k, because all of those changes in y's are going to be different. So the amount of change delta y will be different for each different subinterval. Now, we're going to work on this expression a little bit. So play some algebra games. We're going to factor out a delta x squared out of the two terms that are under that square root. That'll leave us 1 as the first term plus delta y sub k squared over delta x squared. Okay, remember that factoring is like dividing. And you could double check the algebra there. If you multiply delta x squared into the two terms, you'd end up with delta x squared plus delta y sub k squared. Now, change in y over change in x. Okay, let's go back and look at the picture. Change in y over change in x. That is the slope of that line segment. The mean value theorem for derivatives says that there is, if our function is continuous, which it is, then there's got to be some point in the interval between these endpoints, some point in here where the tangent line would be parallel to the secant line. That tangent line slope is f prime, and then the point of tangency we're going to let be the sample point for that interval. So sample point x sub k. So according to the mean value theorem for derivatives, there is some point x sub k for which f prime of x sub k is equal to the change in y over change in x. I say that so that we can rewrite that part. Alright, L is going to equal to the sum from 1 to n of, now I'm going to take a square root of delta x squared, have delta x times 1 plus, now rewriting that as delta y sub k over delta x all squared. And I know that delta y over delta x is equal to the derivative, so I can make that substitution. So 1 plus f prime of sample point x sub k, and that is squared. All of that's under the square root, and we're multiplying by that square root by delta x. Alright, so again, this is just an approximation. If you think back to how we've done so many things in calculus, we take a look at finding an approximation, and we realize that if we have smaller subintervals, our approximation is better. So if you squeeze in more subintervals between A and B, you've got a better approximation. So to get the exact value of the length of this curve, we're going to take the limit as n approaches infinity of that. So L will equal the limit as n approaches infinity of the sum from k equal 1 to n of the square root 1 plus f prime sample point x sub k squared delta x. And then when we have a limit of a sum, we recognize that as a definite integral. So the length of a curve can be calculated by finding a definite integral over the interval from a to b of the square root 1 plus f prime of x squared dx.